We'll start with the webinar now. So before starting, I just want to say very welcome to everyone for joining us today in this fifth webinar in the series of Osmosis Advances from Papers to Practice. Today we have our colleague Dr. Pietro Lubello. I will read a brief summary of the Pietro's CV. So Pietro is a research fellow at the UCL Energy Institute, specializing in energy modeling for sustainable development. His main research interests are in national energy system models and also the role of modeling in planning and policymaking, with a special focus on methods for addressing uncertainty and enhancing inclusiveness. So, for the specific case of Kenya, Pedro has collaborated extensively with the Ministry of Energy, with EPRA, KPLC, and other stakeholders on projects including the Kenya National E-Cooking Strategy, the co-development of power, and whole energy system models analysis of the national green hydrogen strategy in that country. He has a background in energy engineering, and also he earned his PhD from the University of Florence in Italy. So for today, Pietro will be providing a presentation on introducing a geospatial energy model for utility scale solar and wind power build out in Kenya. So, Pietro, once again, thank you so much for having this um, initiative for supporting the energy modeling community and to be today with us in this insightful presentation. So, Pietro, the floor is yours, and thank you so much once again.
Thank you very much, Fernando, for the introduction. So I want to repeat myself. I'll just say that the webinar of today, so the title of this webinar is taken from one of the two papers that we are actually going to focus on today. And I'll start just by giving a brief introduction of the activities that we've been doing on power sector modeling in Kenya. I would start by saying that the aim of what we do, I would say, is twofold. From on one side, we have like the development of open source tools that can be adopted by in-country planners and policymakers. So we're trying to make tools that are policy relevant and can actually be applied in the context we work in. And then at the same time, while doing so, we try to contribute to the dialogue around power system planning in Kenya. And to do so, we have this process that I usually divide in 3 steps. So the first one was about developing a modeling framework that was suitable for the type of analysis that was necessary and was requested by the stakeholders we work with in Kenya. And to answer to this request, we developed this soft linking methodology between OSeMOSYS and FlexTool. The second step then was to improve the geospatial description of solar and wind resources in this type of models using what we call model supply regions. And we will we will talk a little bit more about this in the following slides. And then the third step is recognizing that in all these analyses that we do, uncertainty plays a big role. And so there are methods to embrace this deep uncertainty. For example, the one that we are currently applying in Kenya is the robust decision-making approach. However, the focus of today's webinar is just on the first 2 steps that are associated to 2 papers. So this webinar series is called From Papers to Practice. So I thought it was worth just briefly introducing the 2 papers I've used as a reference for this presentation. So the first step is associated to a paper that was published in early 2024. It's the Chiara et al. Paper for reference in the next slides. And it's really about setting up the methodology, as I mentioned before, and the linking between OSeMOSYS and FlexTool. While the second paper was published later in the same year, in 2024, It was published in Said Report Sustainability, and it's about the introduction of model supply region in order to improve the geospatial description of solar and wind resources. And it's the paper that gives the title to the webinar today. And I will make reference to that paper by calling it Millot et al. So as you can notice, I'm not the first author in none of the two papers, but I've been a key contributor in both of them. So I'm the second author in both of the papers. We just thought that the surnames of the other authors were better, and so you don't see my surname in them. I also need to mention that both papers are a very close collaboration with the Kenyan government, and in particular, the Least Cost Power Development Plan team, which is made of the Ministry of Energy, the regulator, which is EPRA, the power utility, that is KPLC or Kenya Power, and then other organizations and parastatal entities that, I mean, you can see all the symbols at the bottom of the slide. Another key contributor has been Strathmore University, one of our partners in Kenya. And then for the second paper is the result of a collaboration with WRI Africa. So it was worth mentioning this as well. So the first point, which is linked to the first paper, is why do we need to link a capacity expansion model like OSeMOSYS with a production cost model like FlexTool? This, I would say, is standard procedure in the literature. Is quite widely recognized that to better estimate the flexibility requirements, a capacity expansion model basically is not enough because of the necessary simplifications that we need to introduce in this type of models. So, for example, because of the use of time slices. On the other hand, production cost models like IRENA's FlexTool can work at a finer time resolution. They can consider reliability constraints that cannot be included in OSeMOSYS, but they are often too complex to include also the expansion planning in the same tool, which is a possible approach, but it really depends on the context you're working in. So in our case, the soft linking procedure is basically involves running OSeMOSYS first time, and then running FlexTool for a series of marker years, where we basically want to check more in detail how the power system is behaving. So in the case of the two papers that we've published, we've looked at 2030, 2040, and 2050. And we start by running FlexTool in dispatch mode. We check if there are any flexibility issues. If there are no flexibility issues, it means that OSeMOSYS have been able to identify a capacity mix that is can meet all the requirements of the power system, so we move to the next marker year. Otherwise, we run FlexTool in investment mode in order to identify the additional capacity that might be needed. And then we check again for flexibility issues, and we iterate in this way for all the marker years. Of course, I mean, this is a webinar series focused on OSeMOSYS, so you probably all know about the input data that are required by a model like OSeMOSYS. So we need demand projection. We need to describe the technology options, so capacity, cost, efficiencies, etc., the fuel cost. And then for FlexTool, we need a little bit more information to identify the power system requirements, while also for OSeMOSYS, we have some specific input data. And it's the case, for example, for the time slices structure that is not used by FlexTool, of course. In both papers that we've published, we've considered two demand scenarios. The first one, which is like the reference demand scenario, which is the one commonly used by the planning team in Kenya. And then we've considered the second high demand scenario that is inspired by the Vision 2030 plan, which is something that was introduced in Kenya in 2008, I believe. And then it's a very ambitious plan that has very ambitious targets for development in Kenya, and that would take Kenya to reach a peak demand that we estimate to be between 20 and 25 gigawatt. The second bit that is key in this type of analysis is to understand what are the capacity constraints that we need to add in the model. So, of course, we will have some residual capacity, which is made of the power plants that are already built and that have a certain retirement date. And then we have what we call identified capacity, which is made of a list of power plants that have already been committed or that have been planned to be built at a certain point in usually the medium term. And this is based on the least cost power development plan, and is made of several different types of power plants. And you can see in the figure that this includes geothermal, for example. Then we have some fossil capacity, hydro, and some solar and wind, as well as batteries and nuclear. Although this is changing, but that's another story. We then have some additional potential that is uncertain and is based on the resources that are available in country. And this is where I will be presenting the two papers in parallel from a certain point of view. And this is where the two analyses actually differ, is the way we describe this additional potential. So for geothermal and hydro, this doesn't change much. There is a certain capacity that has been identified for geothermal power that could be expanded in country. There is not much extra potential for hydro. So there is potential for like small scale hydro, but for larger scale plants, Kenya has almost has used most of the resources available. The big question remains what to do with the PV and wind, basically, so for solar and wind. The way we did this in the first paper was to consider in the model just one generic technology for solar and one generic technology for wind, with a very high potential, right? There is around 15, we had estimated that to be around 15 gigawatt for both sources. Now, this is not very precise and doesn't give any information on where these resources are located within the country. So what we did in the second work was to introduce these model supply regions as defined in a paper published by Sterle et al. In 2022, which is, this publication is a big data set for the entire African continent and defines these model supply regions for solar and wind resources for all the countries in the continent. These regions are then aggregated, clustered in 10 bigger regions, 10 for solar and 10 for wind, that represent the 10 best regions for the two type of resources. In defining them, several exclusion criteria are considered. So we consider conflicting land use, unfavorable slope, protected areas, high population densities, and existing roads, etc. And all these exclusion criteria can be introduced or removed depending on the needs of the type of analysis, because all the code to obtain these 10 clusters is openly available to anyone interested in replicating this for any country in Africa. A first thing that we can notice is that solar resources tend to be closer to where the existing grid is, while for wind, as you can see in the image, the resources tend to be farther away from the grid in the northern areas of Kenya, where it's more costly to expand the grid to reach those resources. And this is justified by the fact that solar is quite heavily spread over Kenya. So there are not big variations in like the capacity factor and the amount of energy produced by the power plants. While for wind, there are very big differences in the capacity factor that are available around the region of Lake Turkana with respect to the rest of the country. So these regions are already telling us that it is worth to expand the grid to reach the northern regions for to reach the best wind resources. In terms of results, the results are quite well aligned for both papers. We're just going to look, for the sake of brevity, to the second paper. And in general, we see that geothermal and wind play a major role in both demand scenarios considered, so S1 and S2. While for solar, we see that it tends to ramp up just only after 2040, and it's really helped by the declining cost of batteries that after 2040 really helped to unlock the solar potential in country. The second big results that we can observe is that we have a system that is almost 100% renewable energy, especially for the low demand scenario. This is true. And it's true on a production basis. But we still see natural gas being built as a backup capacity in the system. So we have a significant contribution from natural gas in terms of capacity installed. You can see the capacity on the first two graphs on the left-hand side, while the production is on the right-hand side. And this thing about natural gas is quite relevant for Kenya, and is something that we are currently investigating more in detail. And the main reason is that Kenya does not have a natural gas infrastructure at all at the moment. So a model identifying natural gas as really key for the future of the power system really should take into account also the cost of developing this infrastructure and the risk of having stranded assets in the near future. So we believe that this remains an open question, whether Kenya can or do without natural gas in the system. And the uncertainty analysis really helps investigating this in more detail. For solar and wind resources, the key results that we got is that the order of selection of these 10 regions that we have defined is non-trivial. And with non-trivial, we mean that the regions are picked in an order that is not simply based on the average capacity factor, so on the resource strength, or on the least cost resources, but it's really the interplay of these elements and the temporal profile, how the temporal profile of that specific resource matches the demand profile that define the order of selection of the regions. And this is quite interesting because we have a model that is a single node model in OSeMOSYS, right? So we don't have any regions. So it's a relatively simple model that can run on a laptop. But by working with the data inputs and defining these 10 regions that are basically just 10 technologies for solar and 10 technologies for wind in the model, by not increasing the complexity of the model too much, we get some more information on the best locations on where to position the solar and wind power plants. And this information is a non-trivial information. So there is some value added in actually implementing this methodology. And as I mentioned before, everything is based on open source data, and the methodology is available. The code to replicate this methodology is openly available, and it can be extended to African countries. And recently, a similar data set has been published also for South American countries. And so it can also be extended to South America, the same approach. The results here basically show, again, we see that solar starts to play a role in the system after 2040 in both demand scenario, S1 and S2, while wind really starts from 2025. So as soon as it is available, it starts building it. And then we see more in detail in the two figures here, the order in which the various regions are selected by the OSeMOSYS model. And finally, the other result, this is, I would say, a result more of the first paper, but then we have replicated the same analysis in the second one, so it holds for the second one as well, is that FlexTool is actually needed as OSeMOSYS would lose some capacity requirements, right? So FlexTool identifies additional capacity requirements, In 2030, we tend to see only a lack of inertia, but in 2050, we see high levels of both curtailment and loss of load. In general, between 2 and 3 gigawatt of extra capacity are identified by FlexTool, both to cover base load and flexibility requirements. And so really for high variable renewable energy shares, the linking between a capacity expansion model and a production cost model is needed. The figures on the left show the additional capacity identified for 2030 in blue. So in both the low demand and high demand scenario, we see additional capacity required. And I mean, this additional capacity is covered by hydro resources and natural gas, while in 2050, the additional capacity is again covered by hydro and natural gas, but also from nuclear. While on the right-hand side, we see a dispatch profile as identified on an hourly basis, as identified by FlexTool. And we can see that wind is playing like a key role in the first 2 days. And then we have a few days in the graph represented here of low wind production. And we really see some hydro kicking in and a lot of natural gas as well. However, we still end up in the system with some loss of load that is not covered. And this depends on, of course, how FlexTool is balanced, but it can be that the cost optimal solution is to still have a little bit of loss of load. While we see a lot of curtailed power in the days of high wind production, because it's basically solar that is curtailed around midday. To conclude, some next steps. So for Kenya, as I mentioned before, we're working on deep uncertainty methods applied to power system planning, and we are extending the collaboration with all the Kenyan stakeholders that we've been working with in the last 3 years. We're not working just on the power system, but we are also working on the whole energy system. We have another osmosis model that covers all the demand sectors as well as the upstream sector. So it represents the entire energy system for Kenya. And we are really working towards increasing the policy relevance of our modeling tools, trying to have them embedded into the processes, the planning processes and the policymaking processes in Kenya. And one of the key questions, and I've talked about this already, that we are investigating at the moment is whether there is a role for natural gas in the Kenyan power system in the future. In terms of next steps for model supply regions, we are currently working on expanding the approach to other countries. We're working on extreme weather events in Zambia by using a similar methodology to the one introduced today. And then, as I mentioned, we have this data set for South America, and we are looking into using the model supply regions also for power system planning in Bolivia. This is everything from my side, so thank you very much. And I'd be happy to take a few questions, but I would also be happy to take any other question after the webinar if you're curious about something. Thank you very much again.
Thank you so much, Pietro, for this very strong and very insightful presentation. As I mentioned, I have had the opportunity to not to read in a great depth the papers, but I know that the quality is quite high. So thank you so much for this very good presentation. So as Pietro said, the idea now is to open our floor for any questions, doubts, reactions on the different points that were discussed by Pietro. So please feel free to raise your hand and open your microphone for asking your questions. So right now we have one question from our colleague Kane, first of all. So Kane, please go ahead.
Thank you. Yeah, thanks so much, Pietro. Really interesting presentation. I have two questions that maybe just relate to sort of the repeatability and sort of usability of what you've done maybe. My first question would be, about the geospatial aspects of your model and how you like incorporated that does sound like less complicated than like other applications. However, I know that you said it's open source code, but I just wondered how, like replicable it would be and how user friendly it would be for someone else to do that, and maybe just sort of give an idea of the sort of level of understanding someone might need to use that. And then the second question would be, do you have any advice for new users to FlexTool? Maybe Fernando could probably come in on that too, but just in your opinion, having worked with it, how did you find it? And for someone that maybe hasn't used it before, what would you recommend for them to do? But yeah, thanks.
Thanks, Kane, for the questions. Let me go back to to this slide here that maybe helps understanding the process a little bit better. So to reply to your first question, I think that there are different levels at which one could work. So there is a very first level where I think it would be extremely simple to integrate these these regions, these clusters in your model. Because the very first level is just to take, I will be very direct. I mean, just to take an Excel file, basically, the list 10 regions per country for the entire African continent. And you take these 10 regions, and these 10 regions give you the cost, the capital cost of expanding the grid to reach that region in country. And that is a capital cost that you would need to add to the capital cost of your solar power plant or your wind power plant. And then the second step would be to take the capacity factor profile that is provided on an hourly basis for each of the 10 regions. And then you need to map that capacity factor profile to your time slices, if we're talking about OSeMOSYS, as you have probably done already for the other power plants that you have in the model. And then you take the capacity factor profile and you associate one of those capacity factor profiles to one technology in the model. So in the end, it's just about adding 10 additional technology for solar and 10 additional technologies for wind in your OSeMOSYS model. And then you rerun the model exactly as you would have done before with some geospatial information this time, right? Because when you analyze the results, you can map each technology to a specific region in Kenya. And you can say that based on the optimization that OSeMOSYS has done, the best region is that specific region that you get from the results. This is the basic, the base methodology. Then you could also think of regenerating the 10 regions, replicating the procedure that has been applied in the Sterl et al. Publication that I was talking about. And you could decide to replicate this procedure because you want to consider different exclusion criteria in the regions that you actually want to consider. Or because you would like to, instead of having 10 additional technology, you would like to have 20 additional technology, so 20 regions. So I have something with even more detail. Or there are several other reasons for which you might want to adapt this procedure to your specific methodology. But as a starting point, let me say that again, you could just take the data inputs and add 10 extra technologies to your OSeMOSYS model. So I would say it's very, very simple to replicate. On your second question, I am not the FlexTool modeler of these two papers. So I haven't done the FlexTool analysis. For CCG, the person that was doing so is Ariane. So the second paper is called Milo et al. Because Ariane was the other co-lead on the paper, and she was in charge of running FlexTool. What I can say from my side is that not having run the model, it was quite easy to see the results of FlexTool and understand how the model was working. So it was I would say that the experience of the soft linking was quite, I mean, it worked quite well because both models were relatively easy to manage. And this, I think, it's a value added of this methodology with respect of sometimes uses models that have a higher barrier to entry, maybe. But yeah, I can't say much more on the FlexTool side. So you mentioned Fernando, so perhaps Fernando has some experience with FlexTool. Otherwise, if anyone is interested, yeah, I would suggest getting in touch with Ariane, and she could say much more about that.
Do you
Worries.
want to
Thanks.
react on the
Thank you,
answers?
Pietro. No, the answers were great. Yeah, thanks very much. I just thought it'd be nice to get some clarity on that for the wider group, and it also helped me to understand a bit more. So, but yeah, thanks, Pietro, again for the presentation.
Good. Thank you, Kane. I don't have too much to say on top of what Pietro said about FlexTool. Maybe just a couple of small questions about FlexTool. Not sure if you are totally aware of those, but the first one is for the case of FlexTool in specific, was this a single node model the same as in Osmosis, or maybe did you try to represent the regional characteristics in FlexTool?
I'm quite sure that FlexTool had more regions. I think we were considering 4 regions in Kenya because this
Okay.
matches what KPLC does in their planning. However, when we have introduced the model supply regions, I think we have kept the 4 regions in FlexTool because this is really the value added of this methodology, right? Is not to increase the complexity of the model, but give you some insights on the geospatial aspects, right? So as for Osmosis, we've kept just 1 node. I think in FlexTool we have done the same, but considering that as a starting point, we had 4 regions instead of 1.
Okay, and do you know if did you work with version number 2, that cell-based one, or maybe the new one, the third version that is using spine tool, if I remember the name, but it's like you have a proper interface for working with FlexTool. Do you know which version did you use?
Yeah, we've used version 2 because we've started with this methodology back in 2022, I believe.
Okay.
And I don't think that version 3 was yet available. Or
Yeah,
if it was
right.
available, it was just a first version that still had some bugs. So yeah, we've worked with version 2, the Excel-based one.
Okay, perfect. Now I would like to ask other of our colleagues in the meeting if maybe please don't be shy. This is like a good opportunity to ask your question if you maybe didn't understand something, or maybe you want to expand a little bit the knowledge on something about what Pietro mentioned during the presentation. I think this is a good moment for doing it.
As I mentioned before, if anyone wants to reach out, even after this, I'm more than happy to just send me an email. You have my email address here, or you can find it on Google. And yeah, or get in touch on LinkedIn as well. And I'd be happy to then look more in detail at potential expansion of this methodology to other countries, because we had some contacts of people that were interested. I know that someone in Nigeria is thinking of applying these as well. So maybe sometimes people have just more detailed questions that could be discussed in a separate meeting, and I'd be happy to do so.
So the final question that I wanted to ask you, Pietro, is in terms of the policy relevance that you also mentioned as one of the next steps. Could you please maybe elaborate a little bit more on that, on how these studies are being used right now for maybe creating some policy documents, or maybe how the extra work that you are doing in other stages, like for example the robust decision making, maybe they are like totally connected with the generation of some policy instruments or maybe some roadmaps or anything else that is really for the future of the Kenya energy system, and obviously with the support of the officials and government in the country.
Yeah, yeah, thank you for the question. So as I mentioned, started from the we've worked from the very beginning with Kenyan stakeholders, from the Minister of Energy and the power utility and the regulator, etc. And so the idea was from the beginning to develop tools that could be adopted by this team of modelers that is working in Kenya on power system planning, that is called the Least Cost Power Development Plan Team, or LCPDP. And this team develops two reports, one every year and one every 2 years. I believe one is the medium-term plan and the other one is the long-term plan. So they've already used OSeMOSYS for a medium-term plan. So it was, I mean, the model that we developed together was then used to develop this plan. And now with the work on uncertainty, we really believe that this could be the opportunity of informing even higher level stakeholders in the government of future potential pathways for Kenya. And this question around natural gas, I think, is getting more and more relevance as time passes, as kind of as considered before to build like a regasification plant to start importing natural gas. Then the government, as far as I know, have gone through a phase where they really didn't want natural gas at all in the system. So I think it's an open question, and I think we are very well positioned to contribute to that. And all of this is just limited to the power sector, but I've briefly mentioned that we also have this whole energy system model, which is built on top of the power sector model. So it contains the power sector model. And that model was used, for example, for the National E-Cooking Strategy that was published in late 2024. So that is an official document that has been published by the Minister of Energy, and that is based on OSeMOSYS modeling. So from a model that is a very close relative to the one that I've been talking about today. So we have, yeah, as CCG, we offer quite a number of tools that, depending on the various situations, can be adopted, and we really try and make it policy relevant in the sense that I've just explained.
Good, perfect. Just one final curious question now that I recall. Did you consider any potential for offshore wind, or maybe that's something that is totally um, negligible in the context of Kenya?
Yeah, no, that's a good point. We haven't considered that because I believe that the onshore wind resources that Kenya has are really, really great. The Lake Turkana region is a great region for wind. They already have some wind turbines built there. I think is the biggest wind power plant in Africa. So at the moment, I would say that there is no reason for Kenya to consider offshore wind, because on the other hand, the resources that they have on like offshore wind is not that great with respect to other offshore resources. So, and I think also the deepness of the sea just outside of the coast of Kenya. So the sea is quite deep just outside of the coast. So that would make offshore wind quite tricky, unless we're talking about floating offshore, but that is even more costly. So for the moment, I think it's better for Kenya to focus on the onshore wind resources that they have.
Good, perfect. Got it, Pietro. Okay, it looks like at least from our other colleagues in the session, there are no more questions because I don't see any rising hand there. So, okay, I think that we have here. Oh, okay, yeah. Also, just in case, maybe if you are a little shy to ask, maybe we have the bots for asking questions. Just typing. So we have one question from Amadeo Secato. So he says that thank you for the presentation. Just one curiosity I didn't get if in the end the high capex of natural gas infrastructure was already included in the osmosis scenario or no.
Not in the first paper. Yes, in the second one. However, it's quite tricky to estimate properly the cost of the natural gas infrastructure and what share of that infrastructure should be seen from the cost optimization power system tool. So in the end, what we have done in the second paper is that we have included the cost of the regasification terminal, but not the cost, for example, of expanding the natural gas grid, because that would depend on where the power plant is going to be located, for example, right? So we have included that, but up to a certain point, and we think it would be really interesting to actually look at the uncertainty of those costs. And yeah, and so we are considering that in the current phase of the study in Kenya. But thanks for the question. That's a good point.
Yeah, excellent. Thank you, Pietro. But thank you so much, Pietro, for your kindness and the willingness for supporting this initiative once again. I hope that this video of the webinar is going to be very useful for not everyone who was here, but also for other modelers and researchers that probably they will watch the video in the coming days. So thank you for the attendance to everyone, and I hope to see you once again in our next webinar in June. So have an excellent day and see you there in a next opportunity.
Thank you very much for having me. Bye-bye.
Bye bye.